Welcome back to part two in my series where I bring you along in my journey to try to understand from an engineer's perspective some of the main facts and issues behind this climate change discussion. I mentioned in part one, and if you haven't seen part one, I encourage you to look at it. It kind of explains where I'm coming from and what the main issues are that we're trying to address here, so I can get a clearer understanding. In this part, we previously had come up with about 3 or 4 main issues that I'm trying to understand and trying to put numbers to and trying to get a good understanding of how these issues play out. But the biggest one that I had was the whole concept of accuracy. And we talked in the first part about the anomaly graphs from the National Oceanic and Atmospheric Administration showing that there was about a 0.1 degree accuracy shown in the graph since 1880. And my biggest question from an engineering perspective is it feasible to have a 0.1 degree or better accuracy in measuring devices around the globe since 1880? And that was one of my big questions. So what I'm going to try and do in this video is explain some of the things I went through to try and understand this better. And I even went to the extent of developing a software application to kind of prove out some of the theories I had on how this can work. And surprisingly, I learned a lot. And like I mentioned before, a lot of my fears have been dissipated because it turns out there is at least a reasonable hypothesis on how you can get such high accuracy with what it turns out to be some relatively inaccurate devices. So that's what we're going to do in this video, kind of look at the whole topic of accuracy and see how it's at least feasible, conceptually feasible to get in certain circumstances to get that high accuracy. So again, it's required based on that chart and the previous data that there is a capability for measuring global accuracy since 1880 of around plus or minus 0.1 degrees Fahrenheit. So my questions, starting out, the basic one, what is our present equipment accuracy? Can you get 0.1 degrees Fahrenheit accuracy with present equipment, digital equipment, stuff that is probably part of the measurement network around the US and around the world? And the second one, what is the global accuracy? I mean, in the US, based on what I've seen of the measure, there's a lot of devices being used in the US to measure, but what about global accuracy? Is there devices with high accuracy in the Saharan Desert, in Antarctic? Is there the global accuracy of devices back in the 1880s? And to that end, what is the pre-digital or pre-1950s accuracy in the US and globally? When you had, glass mercury thermometers, probably back in the 1800s, was there the same accuracy that you have today? So we're going to try and look at least some of those issues in this video. So my first step is to look at a device I have now in my home, which is a digital indoor-outdoor thermometer, and here's a photo of it, and to try and investigate what's a typical accuracy. And as you can see in this photo, it's got on the top, it's got the outdoor temperature, and when I took this photo, we had just gone through a big cold spell, or cold spell came through, and the outdoor temperature was 16 degrees Fahrenheit and dropping. You can see this arrow going down, and a humidity outside at 50%. And indoor, on the lower side, it was 72 degrees and 32% humidity. So my question was, how accurate is this reading just on a digital device? And my first clue was, if you look at this upper reading for outdoor temperature, it says 16. It doesn't say 16.0 or 16.3. It says 16. So the implication is maybe it's not as accurate to be able to get 1/10 of a degree accuracy. Maybe it has an accuracy of 1 degree, so you can't put a 0.3 because it just doesn't have that accuracy. So what I did is I went to the manufacturer's website and looked at its accuracy specs, and it has a nice table for the accuracy of the temperature measurement. And as you can see here, it depends on the temperature range it's measuring. There's 3 ranges here, 68 to 75. So basically room temperature, it has 1 accuracy. The broad range between freezing and 122, it has a different range. And outside that range, so minus 40 to 32 or 122 to 158, it's got a different range. And you can see the range goes from room temperature, it's pretty accurate, plus or minus 1 degree Fahrenheit. At the broad range, 32 to 122, it's plus or minus 2. And way out in the minus 40 to 32 and above 122, it's plus or minus 4. So if it's 16 degrees out as it's measured here, that fits down here in the plus or minus 4 degrees Fahrenheit. So this 16 is plus or minus 4 degrees Fahrenheit. So it could be 20 degrees actually, or it could be 12 degrees. Or somewhere in between. So it could be anywhere between 12 and 20, but we don't know because it's just not that accurate. Now, a little bit surprising to me was this same chart applies to their high-end $200 plus weather stations. So it seems like if you're going to buy something that's in the hundreds of dollars range, you're going to look at a plus or minus 1 or 2 degrees Fahrenheit accuracy. So that was a little bit surprising to me. I thought with digital devices, you're going to get down into the tenths of a degree or even hundredths of a degree. So my next step was looking at the NOAA, National Oceanic and Atmospheric Administration, or National Weather Service, which is tied to NOAA to do these temperature measurements, and look at their specifications to see what they were saying they need for temperature measurements. So I went to the National Weather Service. This is at the www.nationalweatherservice.noaa.gov, and they have some directives, basically specifications. And there's one document there called the Requirements and Standards for National Weather Service Climate Observations, and it's at that website. It is instruction 10-1302 dated April 20, 2018, and it explains a lot about what they require for making climate observations. And I pulled some pertinent stuff off of that document, the 10-1302. And here in one section it says, this instruction describes the requirements and standards for NWS meteorological climate observations. So this is for climate observations. The standards are for instrument sighting, which turns out to be very important where you put the instrument to measure, exposure, performance, and output data for temperature, precipitation, soil temperature, and evaporation. Now, interestingly, it says if standards cannot be met by the equipment in place, then the standards should be achieved when stations are changed, equipment is installed, programs are modified, or new stations are established. So you can see here, there is some leeway for a device. It doesn't have to meet the standards in this document, but it should be achieved when you change something about that station. So you can see there's a little bit of wiggle room here for accuracy, which is good to keep in mind. So whatever's in here may or may not pertain to any particular station. And it also says the standards for instrument performance, exposure, and data output in this instruction will support the recommendations of the WMO, World Meteorological Organization, for a climate observing program. So all of this seems to say that these requirements apply for measuring climate. Now, they have a few pages into this a accuracy chart, very similar to what we saw with the manufacturer's chart for my indoor-outdoor thermometer, and it's called Air Temperature Measurement Performance Standards. And again, it depends on the range that you're measuring. And they have maximum, minimum, and current reading. Reference temperature minus 30 has one accuracy requirement, plus 50, plus 120. And you can see all of the accuracy requirements are again between 1 or 2 degrees Fahrenheit. And you can see this is Fahrenheit, 1 or 2 degrees, so it matches up quite well with this, except for the broad range where it's plus or minus 4 for this particular device. So we seem to be narrowing down where we want a plus or minus 1 or 2 degrees accuracy. And here there's a little bit of wiggle room too for percent confidence. So it's not 100% confident that you're going to get that accuracy, but it's kind of pointing to a 1 to 2 degree Fahrenheit requirement. So we're starting to see that, yeah, the devices are probably in a 1 or 2 degrees Fahrenheit, at least for the requirements for these climate observations. So again, there is another section where it addresses what the World Meteorological Organization says. And in this National Weather Service document, in section 4.1.3, General Instruments, it says the WMO suggests, again it says suggests, ordinary thermometers be able to measure with high certainty in the range of minus 20 to plus 115 Fahrenheit with maximum error less than 0.4 degrees. So now we're tighter than the 1 to 2. We're down to 0.4. But the next line, it says, in practice, it may not be economical to provide thermometers that meet this performance goal. And we've kind of seen that. We've seen in my device, we're talking 1 to 4 degrees, right? So they're recognizing it's probably going to be expensive to get a more accurate device, but it says less expensive thermometers calibrated against a laboratory standard may be used for these NWS climate purposes, provided they comply with the performance requirement identified in Table 4.1, which is this. So again, they're saying even though the WMO suggests a 0.4, we require that it's 1 to 2 degrees plus or minus Fahrenheit, okay? So again, we're pointing back to the 1 or 2 degrees because they recognize that it's probably not economical to get above that 1 or 2 degrees. And again, if standards cannot be met by equipment in place, then the standard should be achieved when stations are changed. So again, they want 1 or 2 degrees, but for any particular measuring equipment, it doesn't have to be that until it's changed, okay? So, my big question became, how can you have devices that are accurate 1 to 2 degrees Fahrenheit provide global measurements with an accuracy of 0.1 degrees Fahrenheit or better, right? How can you get that chart, the NOAA chart, if your devices are all 1 or 2 degrees Fahrenheit? And honestly, that has bothered me for a long time. I never really looked into it. It was kind of in the back of my mind saying, wait a minute, that doesn't make sense. How can you have inaccurate devices, but globally you're expecting it 1/10 of a degree accurate since 1880, right? So that has always puzzled me. And at one point it occurred to me, maybe there is an assumption of a random distribution of accuracies. In other words, say some devices are reading high by 1 degree, others are reading low by 1 degree, and those errors will average out to be close to 0 error. So, for example, let's say I've got 2 devices, and they're both measuring an actual temperature of 51 degrees Fahrenheit. And let's say one of them measures 52, which is 1 degree high, and the other measures 50, which is 1 degree low. If you take the average of those, you will get the exact right answer. 52 plus 50 divided by 2 equals 51. So maybe, again, if you assume that there's the same number of high readings and as there are the low readings, and you can average them out, maybe you can get an accurate reading with inaccurate devices, right? I mean, the extension of that, let's say you're reading 10 degrees high, which means 61, and this one's reading 10 degrees low, those two will average out to 51. But again, it's making a big assumption that you're having a balanced reading, high and low, that will average out to the correct answer. So that got me interested, and what I did was I actually wrote a software program, which I have explaining in another series on how I wrote that program. And I developed that software to try and help me answer the question, can you generate a bunch of random measurements with a big field of devices? Say you've got 1,000 devices and they're all giving random measurements inside this range of 1 or 2 degrees Fahrenheit accuracy. Can you get an accurate measurement with all these random measurements for all of the devices? So what I did is I did a simulator, a software simulator. And I used an actual temperature of 52 degrees Fahrenheit, which it turns out is, according to NOAA, what they believe to be, in the 20th century, the average global land temperature comes out to one number, which is 52 degrees. So I just chose that as the actual temperature that all of these 1,000 devices are reading. So I simulated 1,000 devices that are reading or should be reading 52 degrees, but they are inaccurate. Their accuracy is plus or minus 2 degrees, which means they should have random measurements between 50 degrees and 54 degrees, since 52 minus 2 is 50 and 52 plus 2 is 54. So I kind of simulated 1,000 devices reading random numbers between 50 and 54 and took the average to see if I could get close to 52. And what I did is I simulated not only one reading of 1,000 devices, but I simulated that we did that one reading of all devices, but did it one day a year for 1 year. So in other words, I did 1,000 devices, took the average, did 1,000 more, took the next average, 1,000 more, and so on, as if I was doing it once a day for 1 year. So I took 365 averages of 1,000 device readings, random device readings, and averaged that all together to see if I could get close to 52 degrees Fahrenheit. Now in the next video in the series, in part 3, we're going to look at the results. We're going to see the software simulator in action and see what results we get. And then after that, we're going to take a little bit closer look at actual device accuracies. We're going to look at some technical papers and some more info on exactly a little bit more about what we can expect for actual device accuracy. So I encourage you to stick around and join me in part 3. And if you like this, hit the like button and subscribe so you can get notified of the next videos. Take care and have a really good day. Thanks.